For most of human history, the idea of worlds beyond our own was confined to imagination, philosophy, and speculation. Ancient thinkers debated whether Earth was unique or part of a much larger cosmos filled with other inhabited worlds. But there was no way to test these ideas. The night sky revealed stars, planets in our own solar system, and distant, glowing points of light. Yet every known world was still within our celestial neighborhood. The possibility of alien worlds remained a mystery without evidence. That changed dramatically in the modern era of astronomy, when technology finally allowed humanity to detect planets orbiting other stars. The search for alien worlds begins with a simple but profound question. Are planets like Earth common in the universe, or is our world a rare exception? For centuries, this question could not be answered. Planets are small, dark, and faint compared to the stars they orbit. Even the largest planets in our solar system are nearly invisible compared to the Sunday. From vast interstellar distances, detecting such objects seemed almost impossible. But as astronomy advanced, scientists developed new methods that transformed this impossible task into one of the most exciting fields in science. The first major breakthrough came indirectly. Instead of seeing planets directly, astronomers began observing their effects on stars. A planet does not orbit a star in isolation. Both the planet and the star orbit a shared center of mass. This means that a star does not remain completely still. Instead, it wobbles slightly due to the gravitational pull of its planets. By carefully measuring these tiny movements, astronomers could infer the presence of unseen worlds. Another method involved studying the light from stars. When a planet passes in front of its star, from our point of view, it blocks a small portion of the star's light. This causes a temporary dip in brightness. These events, known as transits, can reveal not only the presence of a planet, but also its size and orbital period. By analyzing repeated transits, scientists can determine how long a planet takes to orbit its star and estimate its distance from the star. These techniques led to the discovery of thousands of exoplanets, planets orbiting stars outside our solar system. Each discovery expanded our understanding of how common planetary systems are in the universe. What once seemed rare turned out to be extremely common. Planets are not exceptions, they are the rule. Almost every star appears to host at least one planet, and many have multiple worlds orbiting them. Among these discoveries, one of the most important categories is Earth-like planets. These are rocky worlds similar in size and composition to Earth. They are of particular interest because they may have conditions suitable for life. However, finding such planets is only the first step. The more important question is whether they have the right environments to support liquid water, stable atmospheres, and long-term climate stability. This leads to the concept of the habitable zone, often called the Goldilocks zone. This is the region around a star where temperatures are just right for liquid water to exist on a planet's surface. If a planet is too close to its star, it becomes too hot and water evaporates. If it is too far away, it becomes too cold and water freezes. The habitable zone represents a delicate balance where conditions might allow Earth-like environments to exist. The size and location of the habitable zone depend on the type of star. Smaller, cooler stars have habitable zones much closer to them, while larger, hotter stars have habitable zones farther out. This means that not all stars are equally likely to host habitable planets. Red dwarf stars, which are the most common type of star in the galaxy, have narrow habitable zones that are close to the star, while Sun-like stars have wider and more stable zones. As more exoplanets have been discovered, scientists have identified many that lie within these habitable zones. However, being in the habitable zone does not guarantee habitability. A planet must also have the right atmosphere, surface conditions, and chemical composition. Without these factors, even a planet in the perfect orbital location could be completely uninhabitable. One of the most surprising discoveries in exoplanet research is the existence of super-Earths. These are planets that are larger than Earth but smaller than Neptune. They can have masses several times that of Earth and may have a wide range of compositions. Some super-Earths are rocky like Earth, while others may have thick atmospheres or deep oceans. Their diversity makes them one of the most interesting types of exoplanets to study. Super-Earths challenge our understanding of planetary formation. In our solar system, there are no planets in this size range. This suggests that planetary systems can evolve in very different ways depending on their initial conditions. Some super-Earths may have conditions suitable for life, while others may be completely hostile environments with extreme pressures and temperatures. The discovery of exoplanets has also revealed the existence of planetary systems very different from our own. Some stars have planets orbiting extremely close to them, completing an orbit in just a few days. These planets are often tidally locked, meaning one side always faces the star while the other remains in darkness. This creates extreme temperature differences between the day and night sides, leading to unusual atmospheric and geological conditions. Other systems contain giant planets located very close to their stars, known as hot Jupiters. These gas giants challenge traditional models of planetary formation, which suggest that such large planets should form far from their stars. Their existence suggests that planets can migrate over time, moving from their original positions to new orbits due to gravitational interactions. As detection methods improved, scientists began to study not only the presence of exoplanets, but also their physical characteristics. By analyzing the light that passes through a planet's atmosphere during a transit, astronomers can identify the chemical composition of that atmosphere. This technique, known as transmission spectroscopy, allows scientists to detect gases such as water vapor, carbon dioxide, methane, and other molecules that may be important for habitability. These atmospheric studies are crucial for understanding whether a planet could support life. The presence of certain gases, especially in combinations that are difficult to produce without biological processes, may indicate the possibility of life. However, interpreting these signals is extremely complex, and scientists must carefully distinguish between biological and non-biological sources. The study of exoplanets has also revealed that planetary systems are incredibly diverse. Some systems are tightly packed, with multiple planets orbiting close to their star. Others are more spread out, with giant planets dominating the outer regions. This diversity suggests that there is no single model for how planetary systems form or evolve. Despite the vast number of exoplanets discovered so far, we have only begun to explore the galaxy. The Milky Way contains hundreds of billions of stars, each potentially hosting multiple planets. This means that the number of planets in our galaxy alone could be in the trillions. Among these, there may be countless worlds with conditions similar to Earth. The search for alien worlds is not just about finding planets, it is about understanding our place in the universe. Earth is no longer seen as the only possible home for life. Instead, it is one of many potential worlds where life could exist. This shift in perspective has profound implications for science, philosophy, and humanity's view of itself. As technology continues to improve, New missions and telescopes are being developed to study exoplanets in greater detail. These instruments will allow scientists to directly image some exoplanets, study their atmospheres with greater precision, and possibly even detect signs of biological activity. The discovery of alien worlds is still in its early stages, but it has already transformed our understanding of the universe. What once seemed like a single, isolated planet orbiting a single star is now part of a vast and complex system of worlds. Each new discovery adds another piece to the puzzle of how planets form, evolve, and potentially support life. In the grand cosmic landscape, Earth is no longer the only known world of its kind. It is part of a much larger population of planets scattered throughout the galaxy. Some may be barren and lifeless. Others may be extreme and hostile. But some may hold the conditions necessary for life, waiting to be discovered. The journey to find these worlds is just beginning, and each step brings us closer to answering one of the most profound questions in science: whether we are alone in the universe or one of many living worlds scattered among the stars. The search for alien worlds took a major step forward when astronomers began to realize that not all planets need to be seen directly to be discovered. For centuries, planets were thought of as faint points of reflected light, too small and too dim to be detected beyond our own solar system. But the breakthrough came from a simple idea. Instead of trying to see the planets themselves, scientists could look for the subtle effects they have on the stars they orbit. This shift in thinking transformed exoplanet science from speculation into a precise and rapidly advancing field. One of the most important concepts in this search is the habitable zone, often called the Goldilocks zone. This is the region around a star where conditions might allow liquid water to exist on the surface of a planet. Liquid water is considered one of the most important ingredients for life as we know it. It acts as a solvent for chemical reactions, supports complex molecular interactions, and provides a stable environment for biological processes. Without liquid water, life in the form we understand becomes extremely unlikely. The habitable zone is not a fixed distance. It depends entirely on the type of star. Stars vary widely in size, temperature, and brightness. A small, cool red dwarf star emits far less energy than a star like our Sun. As a result, its habitable zone is located much closer to the star. In contrast, a larger and hotter star pushes its habitable zone much farther out. This means that the potential for habitable planets exists across a wide range of stellar environments, not just around Sun-like stars. The idea of the habitable zone is based on energy balance. A planet receives energy from its star and loses energy back into space. If the balance is too hot, water evaporates into gas. If it is too cold, water freezes into ice. The habitable zone represents the region where this balance allows water to remain in liquid form. However, this concept is only a starting point. Real planetary habitability depends on many additional factors beyond temperature alone. For example, a planet's atmosphere plays a crucial role in regulating surface conditions. A thick atmosphere can trap heat through the greenhouse effect, raising surface temperatures even if the planet is far from its star. Conversely, a thin atmosphere may fail to retain heat, causing extreme temperature variations. The composition of the atmosphere also matters. Gases like carbon dioxide and methane can strongly influence climate, while oxygen and nitrogen can support different chemical environments. Another important factor is the planet's orbital stability. A planet with a highly elliptical orbit may move in and out of the habitable zone during its year, causing extreme seasonal changes. A stable, nearly circular orbit provides more consistent conditions for potential life. The presence of other planets in the system can also affect orbital stability through gravitational interactions, making some systems more chaotic than others. The habitable zone also depends on time. Stars change over their lifetimes. As a star ages, it gradually becomes brighter and hotter. This means that the habitable zone slowly moves outward over billions of years. A planet that is currently in the habitable zone may not have always been there, and it may not remain there in the future. This introduces the idea of a continuously habitable zone, where conditions remain stable for long enough periods to allow life to develop and evolve. When astronomers began applying the habitable zone concept to newly discovered exoplanets, they identified many interesting candidates. Some of these planets are located within their star's habitable zone and have sizes similar to Earth. These worlds are among the most promising targets in the search for life beyond our solar system. However, being in the habitable zone does not guarantee that a planet is truly habitable. It only indicates that the basic conditions for liquid water might exist. One of the key discoveries in exoplanet research is that planetary systems are far more diverse than previously imagined. In our solar system, the habitable zone contains Earth, a rocky planet with a stable atmosphere and abundant liquid water. But in other systems, the situation can be very different. Some planets in the habitable zone may be completely covered in thick clouds, making it impossible to observe their surfaces directly. Others may have runaway greenhouse effects, turning them into extremely hot and hostile environments. There are also planets that challenge our traditional definition of habitability. Some large rocky planets, known as super-Earths, are much more massive than Earth, but still potentially rocky in composition. These planets may have stronger gravity, thicker atmospheres, and different geological activity. Their environments could be very different from Earth, but still potentially capable of supporting some form of life. Super-Earths are particularly interesting because they may be more common than Earth-sized planets. Many of the exoplanets discovered so far fall into this category. Their larger size means they are easier to detect, but it also raises important questions about their internal structure. A super-Earth could have a deep global ocean, a thick atmosphere, or a dense rocky surface with intense volcanic activity. Each of these possibilities has different implications for habitability. Another important category of exoplanets includes those orbiting red dwarf stars. These stars are the most common type in the galaxy, and many of them host planets in their habitable zones. However, red dwarf systems present unique challenges. Because the habitable zone is so close to the star, planets in this region are often tidally locked. This means one side of the planet always faces the star, while the other side remains in permanent darkness. Tidal locking creates extreme environmental conditions. The day side of the planet may be extremely hot, while the night side is freezing cold. However, atmospheric circulation and ocean currents, if present, could help distribute heat more evenly across the planet. This means that even tidally locked worlds might still have regions with moderate temperatures, potentially suitable for life. Red dwarf stars also produce strong stellar flares, which can emit bursts of radiation that may affect planetary atmospheres. These flares can strip away atmospheric gases or alter chemical compositions, making long-term habitability more uncertain. Despite these challenges, red dwarf systems remain important targets in the search for alien worlds because of their abundance. As detection methods improve, scientists are beginning to study not just the presence of exoplanets, but also their physical and chemical properties. One of the most powerful tools for this is transit spectroscopy. When a planet passes in front of its star, some of the starlight passes through the planet's atmosphere before reaching Earth. By analyzing this light, scientists can detect the presence of specific molecules in the atmosphere. This technique allows astronomers to identify gases such as water vapor, carbon dioxide, methane, and other compounds. These molecules can provide clues about the planet's climate and potential habitability. In some cases, unusual combinations of gases may suggest chemical processes that are difficult to explain without biological activity. However, interpreting these signals is extremely complex, and scientists must carefully rule out non-biological explanations. The study of exoplanets has also revealed that planetary formation is a highly dynamic process. Planets do not always remain in the positions where they formed. Gravitational interactions between planets and with the protoplanetary disk can cause planets to migrate inward or outward over time. This migration can dramatically reshape planetary systems, leading to configurations very different from our own solar system. Some giant planets have been found extremely close to their stars, in regions where they could not have formed in place. These hot Jupiters likely migrated inward after forming farther out in the system. Their presence can also affect the formation and stability of smaller rocky planets in the same system, potentially influencing the chances of habitable worlds forming. The diversity of exoplanets suggests that the universe is filled with a wide range of environments. Some planets may be completely barren, others may be dominated by extreme weather systems, and some may have conditions similar to Earth. This diversity is one of the most important discoveries in modern astronomy, as it shows that planetary systems are not uniform but highly varied. The habitable zone remains a useful concept, but it is only one part of a much larger picture. True habitability depends on a combination of factors, including atmosphere, geology, magnetic fields, orbital stability, and stellar activity. A planet must maintain a delicate balance of these conditions over long periods of time to support life as we know it. As more exoplanets are discovered, scientists are building a statistical understanding of how common different types of planets are. This helps estimate how many potentially habitable worlds might exist in the galaxy. While we have only identified a small fraction of the total number of planets in the Milky Way, current evidence suggests that habitable zone planets may be relatively common. The search for alien worlds is therefore not just about finding individual planets. It is about understanding the broader patterns of planetary formation and evolution. By studying how planets are distributed across different types of stars and environments, scientists can begin to answer deeper questions about the likelihood of life elsewhere in the universe. Each new discovery adds to this growing picture. Every planet found in the habitable zone, every atmosphere analyzed, and every unusual system observed helps refine our understanding of where life might exist. The universe is revealing itself as a vast and complex collection of worlds, each with its own history and potential. In this ongoing exploration, the habitable zone serves as a guidepost, pointing us toward regions where life might be possible. But it is only the beginning. The true nature of alien worlds will be revealed through continued observation, analysis, and discovery, as humanity extends its reach into the galaxy and uncovers the diversity of planets that exist beyond our own solar system. As the search for alien worlds expanded beyond simple detection, scientists began to realize that not all planets can be understood through a single category. The universe does not produce only Earth-like worlds or gas giants similar to Jupiter and Saturn. Instead, it creates an enormous diversity of planetary types, each shaped by different conditions during formation and evolution. Among the most important discoveries in this growing catalogue of exoplanets are rocky worlds and super-Earths, two categories that challenge our understanding of what a planet can be and how it might support life. Rocky worlds are planets primarily composed of silicate rock and metal, similar in structure to Earth, Venus, Mars, and Mercury in our own solar system. These planets have solid surfaces, and their environments are shaped by geology, atmosphere, and temperature. In the search for life beyond Earth, rocky planets are considered the most promising candidates, because life, as we know it, requires a stable surface and a long-term environment where complex chemistry can develop. The formation of rocky planets begins in the early stages of a planetary system. Around young stars, a disk of gas and dust, known as a protoplanetary disk, surrounds the star. Within this disk, tiny particles collide and stick together, gradually forming larger and larger bodies. Over millions of years, these bodies grow through a process called accretion, eventually becoming planetesimals and then full-sized planets. The inner regions of the disk, where temperatures are higher, tend to form rocky planets because volatile materials such as water, ice, and methane cannot easily survive there. This process explains why rocky planets are typically found closer to their stars, while gas giants form farther out where cooler temperatures allow volatile compounds to accumulate. However, exoplanet discoveries have shown that this simple picture is not always accurate. Planetary migration and gravitational interactions can move planets from their original formation locations, creating systems that look very different from our own solar system. Rocky exoplanets vary widely in size and composition. Some are similar to Earth in mass and radius, while others are significantly larger. This brings us to one of the most important categories in modern exoplanet science, the super-Earth. Super-Earths are planets with masses greater than Earth, but significantly lower than ice giants like Uranus and Neptune. They typically range from about 2 to 10 times the mass of Earth. Despite their name, super-Earths do not necessarily resemble Earth in other ways. They may be rocky, ocean-covered, or have thick gaseous atmospheres, depending on their formation history and environmental conditions. The discovery of super-Earths was surprising because no such planets exist in our solar system. This absence suggested that our planetary system might not be representative of the galaxy as a whole. As more exoplanets were discovered, it became clear that super-Earths are actually one of the most common types of planets in the Milky Way. This realization fundamentally changed our understanding of planetary formation. One of the key questions about super-Earths is whether they are truly rocky. A planet's composition depends on its mass and the materials available during its formation. As planets become more massive, their gravity increases, allowing them to retain thicker atmospheres. This can blur the line between rocky planets and gas-rich mini-Neptunes. Some super-Earths may have solid surfaces beneath dense atmospheres, while others may be dominated by thick layers of gas with no clearly defined surface. The internal structure of a super-Earth is also different from that of Earth. Higher mass means higher pressure in the planet's interior. This can lead to different geological processes, such as stronger volcanic activity or different forms of plate tectonics. Some models suggest that super-Earths may have more active geology than Earth, which could influence their ability to support life by recycling nutrients and maintaining stable climates. However, higher gravity can also create challenges for habitability. On a super-Earth, the increased gravitational force would make everything feel heavier. Mountains might be lower, atmospheres denser, and biological structures potentially more compressed. Life, if it exists on such worlds, would have to adapt to entirely different physical conditions. One of the most important factors in determining whether a rocky planet or super-Earth could support life is its atmosphere. Atmospheres play a crucial role in regulating temperature, protecting the surface from radiation, and enabling chemical reactions. Without an atmosphere, a planet is exposed to the harsh conditions of space, including extreme temperature variations and harmful radiation from its star. The composition of an atmosphere depends on many factors, including volcanic activity, chemical reactions on the surface, and interactions with the host star's radiation. For example, volcanic outgassing can release gases such as carbon dioxide, water vapor, and sulfur compounds. Over time, these gases can build up to form a thick atmosphere, influencing the planet's climate and potential habitability. In some cases, super-Earths may retain thick hydrogen-rich atmospheres, especially if they formed in regions of the protoplanetary disk where gas was abundant. These atmospheres can create strong greenhouse effects, leading to high surface temperatures even if the planet is far from its star. Such conditions may make the surface uninhabitable for Earth-like life, but they could still allow for exotic forms of chemistry in upper atmospheric layers or subsurface environments. Another important aspect of rocky planets and super-Earths is their magnetic field. A magnetic field is generated by the movement of electrically conductive material in a planet's interior, often in a liquid iron core. This magnetic field acts as a shield, protecting the atmosphere from being stripped away by stellar wind and cosmic radiation. On Earth, the magnetic field plays a key role in maintaining a stable environment for life. For super-Earths, the situation is more complex. Their larger size may lead to different internal dynamics. Some models suggest that super-Earths could have stronger magnetic fields due to more vigorous convection in their cores, while others suggest that higher pressure conditions might suppress magnetic activity. The presence or absence of a magnetic field could significantly affect a planet's long-term habitability. The surface conditions of rocky exoplanets can vary dramatically. Some may be dry and barren, like Mars, with thin atmospheres and little geological activity. Others may be volcanically active, with molten lava covering large regions of the surface. Still others may have stable conditions with oceans, continents, and weather systems similar to Earth. One particularly interesting possibility is the existence of water-rich rocky planets. These worlds may have deep global oceans covering their entire surface. In such cases, there may be no exposed land at all. These ocean worlds could potentially support life in their vast liquid environments, although the lack of land could affect nutrient cycles and geological processes. Super-Earths, in particular, may be more likely to host global oceans due to their larger mass and stronger gravity. This could lead to deeper oceans and higher pressures at the seafloor, potentially creating exotic high-pressure environments where unfamiliar forms of chemistry occur. These conditions are very different from Earth, but they expand the range of environments where life might exist. Another important factor in studying rocky exoplanets is their distance from their host star. Planets too close to their star may experience extreme heating, leading to runaway greenhouse effects similar to Venus. Planets too far away may become frozen worlds with thick ice layers and no liquid water on the surface. Only a narrow range of distances allows for stable surface conditions over long periods of time. However, even planets outside this range may still be interesting. Subsurface oceans beneath ice layers could exist on cold worlds, protected from surface conditions by thick layers of ice. Internal heating from radioactive decay or tidal forces could maintain liquid water beneath the surface, creating hidden environments where life might potentially exist. The discovery of rocky exoplanets and super-Earths has also raised important questions about the uniqueness of Earth. For a long time, Earth was assumed to be a typical rocky planet. But the diversity of exoplanets suggests that Earth may be just one example among many possible planetary configurations. Some planets may be more massive, some may have different atmospheric compositions, and others may have entirely different geological processes. This realization has profound implications for the search for life. If rocky planets are common, and if some of them exist in habitable zones, then the number of potentially habitable environments in the galaxy could be extremely large. However, habitability depends on more than just size and location. It requires a long-term balance of many factors that must remain stable over geological timescales. As observational technology continues to improve, scientists are beginning to study the atmospheres of rocky exoplanets in greater detail. Future telescopes will be able to detect smaller planets and analyze their chemical signatures more precisely. This will allow researchers to identify potential biosignatures and better understand the diversity of rocky worlds. In the broader context of planetary science, rocky worlds and super-Earths represent a crucial step in understanding how planets form and evolve. They bridge the gap between small terrestrial planets and larger gas giants, revealing a continuous spectrum of planetary types rather than distinct categories. This spectrum reflects the complex processes that shape planetary systems across the galaxy. Ultimately, the study of rocky exoplanets and super-Earths brings us closer to answering one of the most fundamental questions in science: how common are Earth-like environments in the universe? Each new discovery adds to this picture, revealing a galaxy filled with diverse and dynamic worlds, each with its own potential for complexity and, possibly, life. Among the many types of alien worlds discovered beyond our solar system, none are more intriguing than ocean worlds. These are planets where water is not just a surface feature or a seasonal presence, but a dominant global component that shapes the entire planet. In some cases, ocean worlds may be entirely covered by deep, uninterrupted seas that stretch across the globe without a single continent breaking the surface. These planets challenge our Earth-centered view of habitability and open up entirely new possibilities for where life might exist in the universe. The idea of an ocean world begins with a simple but powerful ingredient: water. On Earth, water is essential for life. It supports biological chemistry, regulates climate, and provides a medium for complex interactions at the molecular level. Because of this, scientists often use the presence of liquid water as a primary indicator of potential habitability. But ocean worlds take this concept to an extreme. Instead of having oceans as one part of a diverse environment that includes land, they may consist almost entirely of water from surface to deep interior layers. Ocean worlds can form in several ways. One possibility is that they originate in regions of a planetary system where water ice is abundant during planet formation. In the outer regions of a protoplanetary disk, temperatures are low enough for water, ammonia, and methane to exist in solid form. Planets forming in these regions can accumulate large amounts of ice. If such a planet later migrates closer to its star or experiences internal heating, that ice can melt into vast global oceans. Another way ocean worlds may form is through volcanic and geological processes. A rocky planet may release water through volcanic outgassing over time, gradually building up an atmosphere and eventually forming oceans. If conditions are right and the planet has enough water, These oceans may become global in scale. In some cases, there may be no exposed land at all, only a continuous layer of water covering the entire surface. One of the most fascinating aspects of ocean worlds is the potential depth of their oceans. On Earth, the deepest known ocean trenches reach depths of around 11 kilometers. On ocean worlds, however, the oceans could be hundreds or even thousands of kilometers deep. Beneath these vast oceans, there may be layers of high-pressure ice or even exotic forms of water that exist only under extreme conditions. At such depths, the environment would be completely unlike anything found on Earth. The structure of an ocean world depends heavily on its mass and composition. Larger planets, especially super-Earths, may be more likely to host deep global oceans due to their strong gravity. This gravity compresses the planet's surface, allowing large amounts of water to accumulate and remain stable over long periods of time. In some cases, the pressure at the bottom of these oceans may be so high that water transforms into different crystalline phases or interacts with rocky material in unusual ways. One of the key questions about ocean worlds is whether they can support life. On Earth, life is found in almost every environment where liquid water exists, from shallow ponds to deep ocean hydrothermal vents. This suggests that if liquid water is present on another world, there is at least a possibility that life could emerge. However, ocean worlds present unique challenges that may affect the development of life. One major challenge is the lack of land. On Earth, land plays an important role in nutrient cycles. Rivers carry minerals from continents into the oceans, supporting marine ecosystems. Volcanic activity on land also contributes gases and chemicals to the atmosphere and oceans. On a planet with no continents, these processes would be very different or absent entirely. This raises questions about how nutrients would circulate in a global ocean and whether sufficient chemical diversity could be maintained to support complex life. Another challenge is the potential isolation of the ocean from the planet's rocky interior. In some ocean worlds, the layer of water may be separated from the rocky core by a thick layer of high-pressure ice. If this is the case, the exchange of minerals between the core and the ocean may be limited. This could restrict the availability of key elements needed for life, such as phosphorus and iron. However, alternative mechanisms such as hydrothermal activity at the ocean floor could still provide energy and nutrients. Despite these challenges, ocean worlds remain some of the most promising candidates for extraterrestrial life. On Earth, some of the most extreme environments, such as deep-sea hydrothermal vents, host thriving ecosystems completely independent of sunlight. These ecosystems rely on chemical energy rather than solar energy. This suggests that life on ocean worlds could potentially exist in similar environments far below the surface, where conditions are stable and protected from harsh space radiation. The discovery of ocean worlds in our solar system has strengthened this possibility. Moons such as Europa and Enceladus are believed to have subsurface oceans beneath their icy crusts. These oceans are kept in a liquid state by tidal heating, which generates internal heat due to gravitational interactions with their parent planets. Although these moons are not exoplanets, they provide important examples of how ocean environments can exist in unexpected places. Exoplanet ocean worlds, however, may be far more diverse and extreme. Some may have shallow global oceans with mild climates, while others may have deep, high-pressure environments with exotic chemistry. The temperature of these oceans depends on the planet's distance from its star and the composition of its atmosphere. A thick atmosphere can trap heat and maintain liquid water even on planets that are relatively far from their star. The atmospheres of ocean worlds play a crucial role in determining their climate. A water-rich atmosphere can create a strong greenhouse effect, stabilizing surface temperatures and preventing the oceans from freezing. However, if the atmosphere is too dense or contains too many greenhouse gases, it could lead to extreme heating and the evaporation of surface water. The balance between these effects determines whether an ocean world remains stable over long periods of time. Another important factor is the interaction between the ocean and the atmosphere. On Earth, this interaction drives weather systems, ocean currents, and climate regulation. On an ocean world, global ocean currents may play a much larger role in distributing heat and nutrients. Without land masses to interrupt these currents, the entire planet could be dominated by large-scale circulation patterns that shape its climate in unique ways. The possibility of life in ocean worlds also depends on energy sources. On Earth, life is powered primarily by sunlight through photosynthesis. However, in deep ocean environments, life can also rely on chemical energy from hydrothermal vents. These vents release minerals and heat from the planet's interior, creating localized environments rich in chemical energy. If similar systems exist on ocean worlds, they could provide the necessary energy for life to develop and sustain itself. One of the most intriguing possibilities is that ocean worlds could host entirely different forms of life compared to Earth. Without land or sunlight reaching the ocean floor, life may evolve in ways that are completely adapted to deep water environments. These organisms might rely on chemical gradients, thermal energy, or other processes that are not dominant in Earth's surface ecosystems. Detecting ocean worlds around distant stars is a major challenge. Because these planets are far away, we cannot directly observe their surfaces in detail. Instead, scientists rely on indirect methods such as transit observations and atmospheric analysis. When a planet passes in front of its star, small changes in the star's light can reveal information about the planet's size and atmospheric composition. In some cases, the density of a planet can provide clues about whether it is an ocean world. A planet with a lower density than expected for a rocky world may contain large amounts of water. However, distinguishing between a water-rich planet and one with a thick gaseous atmosphere can be difficult. More precise measurements and future telescopes will be needed to confirm the nature of these worlds. The study of ocean worlds also has implications for understanding planetary evolution. These planets represent a different pathway of development compared to Earth-like worlds. Instead of forming with a balance of land and water, they may begin with an overwhelming abundance of water that shapes their entire geological and atmospheric history. This leads to planetary systems that are fundamentally different from our own. As more exoplanets are discovered, it is becoming increasingly clear that ocean worlds may be relatively common in the galaxy. This raises the possibility that habitable environments are not limited to Earth-like planets, but may also exist in deep global oceans spread across entire worlds. If this is true, the potential number of habitable environments in the universe could be far greater than previously imagined. Ocean worlds challenge our assumptions about where life can exist. They show that habitability is not restricted to planets with continents, familiar weather patterns, or Earth-like geography. Instead, life may arise in environments that are completely alien to our experience, shaped by deep oceans, high-pressure chemistry, and global circulation systems. In the broader search for alien life, ocean worlds represent one of the most promising and mysterious categories. They expand the definition of what a habitable planet can be and suggest that life may not require Earth-like conditions to emerge. Instead, it may thrive in a wide variety of environments across the galaxy. As exploration continues, ocean worlds will remain at the center of scientific curiosity. They are not just distant planets covered in water. They are potential laboratories for understanding the origins of life, the diversity of planetary systems, and the many ways in which chemistry and physics can combine to create complex environments. In the vast ocean of the cosmos, these worlds remind us that water, one of the simplest and most familiar substances, may also be one of the most important ingredients in the search for life beyond Earth. Beyond the familiar concept of oceans on Earth and the vast water-covered worlds that may exist across the galaxy, there is another equally fascinating category of planets that challenges our understanding of habitability. These are ice worlds with hidden oceans, planets that appear frozen and lifeless on the surface but may conceal vast liquid seas beneath thick layers of ice. At first glance, they seem like some of the coldest and most inhospitable places in the universe. Yet, beneath their frozen exteriors, they may contain environments capable of supporting life in ways that are completely hidden from direct observation. Ice worlds form in the colder regions of planetary systems, far from the warmth of their host stars. In these outer regions, temperatures are low enough for water, methane, ammonia, and other volatile compounds to freeze solid. During the early stages of planetary formation, large amounts of ice can accumulate in these regions, allowing planets and moons to develop thick icy crusts. These bodies may initially form as frozen worlds, with solid surfaces composed primarily of water ice mixed with rocky material. However, the story of an ice world does not end with its frozen surface. Many of these planets and moons experience internal heating, which can dramatically alter their internal structure. This heating can come from several sources. One of the most important is radioactive decay within the planet's rocky core. As unstable isotopes decay over time, they release heat that warms the interior of the planet. Another powerful source of heating is tidal forces, which occur when a planet or moon is gravitationally stretched and compressed by the presence of a nearby massive object, such as a giant planet or another moon. Tidal heating is especially important in systems where icy moons orbit large gas giants. As the moon moves along its orbit, the gravitational pull from the planet varies, causing the moon to flex slightly. This constant flexing generates internal friction which produces heat. Over long periods of time, this heat can be sufficient to melt large amounts of ice beneath the surface, forming subsurface oceans that are completely hidden from view. The existence of subsurface oceans beneath ice layers transforms our understanding of where liquid water can exist. On Earth, liquid water is generally associated with surface conditions and atmospheric pressure. But on ice worlds, water can exist in a completely different environment, sealed beneath kilometers or even tens of kilometers of ice. These oceans are shielded from the harsh conditions of space, including radiation, micrometeorite impacts, and extreme temperature fluctuations. One of the most intriguing aspects of these hidden oceans is their potential stability over long timescales. Because the ice layer acts as an insulating barrier, the liquid water beneath it can remain stable for millions or even billions of years. This creates a long-lived environment where chemical processes can occur relatively undisturbed. In some cases, the pressure at the bottom of these oceans may be extremely high, leading to exotic forms of ice and water interactions that do not exist on Earth. The internal structure of an ice world with a subsurface ocean is layered and complex. At the top is a frozen crust of water ice. Beneath this crust lies a liquid ocean, potentially hundreds of kilometers deep. Below the ocean may be a rocky core which can interact with the water above it through hydrothermal activity. This interaction between rock and water is particularly important because it can provide chemical energy, heat, and nutrients that may support life. On Earth, similar processes occur at deep-sea hydrothermal vents, where superheated water rich in minerals rises from the ocean floor. These vents support entire ecosystems that do not rely on sunlight. Instead, they depend on chemical energy produced by reactions between seawater and the Earth's interior. If similar hydrothermal systems exist on ice worlds, they could provide a potential energy source for life in subsurface oceans. The idea that life could exist in such hidden environments is one of the most exciting possibilities in modern planetary science. Even though these oceans are completely isolated from sunlight, they may still have all the ingredients necessary for life. Liquid water, chemical energy, and stable environments over long timescales are all present in these systems. The main question is whether the necessary chemical pathways for life to begin and evolve can occur under these conditions. One of the most famous examples of an ice world in our own solar system is Europa, a moon of Jupiter. Europa is covered in a thick shell of ice, but beneath this surface, scientists believe there is a global ocean of liquid water. This ocean is thought to contain more water than all of Earth's oceans combined. The surface of Europa shows signs of cracking and movement, suggesting that the ice layer is not completely rigid, but slowly shifting over time. Another example is Enceladus, a small moon of Saturn. Enceladus has become one of the most important targets in the search for life beyond Earth, because it actively ejects plumes of water vapor and ice particles into space. These plumes originate from a subsurface ocean beneath the icy crust. By analyzing the composition of these plumes, scientists have detected organic molecules and signs of hydrothermal activity, making Enceladus a strong candidate for potential habitability. While these moons are not exoplanets, they provide important analogues for understanding ice worlds elsewhere in the galaxy. If similar processes occur on planets orbiting other stars, then subsurface oceans could be a common feature in the universe. This expands the range of environments where life might exist far beyond the traditional concept of habitable zones on planetary surfaces. The formation of ice worlds with hidden oceans depends on a delicate balance of temperature, composition, and internal heat. A planet must be cold enough on the surface to maintain an ice layer, but warm enough internally to keep water in a liquid state beneath it. This balance can be maintained over long periods through radioactive heating and tidal forces. If the internal heat is too strong, the ice layer may melt completely, turning the planet into a surface ocean world. If it is too weak, the entire planet may freeze solid. The thickness of the ice layer is an important factor in determining the conditions within the subsurface ocean. A thicker ice shell provides better insulation, but also increases pressure on the ocean below. This pressure can lead to the formation of high-pressure ice phases at the bottom of the ocean, which may separate the liquid water from the rocky core. This separation could limit the exchange of nutrients and energy between the core and the ocean, affecting the potential for life. Despite these challenges, subsurface oceans remain one of the most promising environments for extraterrestrial life. One of the key advantages of these environments is their stability. Unlike surface environments, which are exposed to radiation and climate variations, subsurface oceans are protected from external disturbances. This stability could allow life, if it exists, to evolve over very long timescales without being disrupted by catastrophic events. Another advantage is the potential abundance of these environments. Ice is a common material in the outer regions of planetary systems. Many exoplanets and moons are likely to form in these cold regions, suggesting that subsurface oceans could be widespread throughout the galaxy. If even a small fraction of these worlds have the right conditions for life, then the total number of habitable environments could be enormous. Detecting ice worlds with subsurface oceans around distant stars is extremely challenging. Because these oceans are hidden beneath thick ice layers, they cannot be observed directly. Instead, scientists must rely on indirect methods such as studying the planet's density, orbital behavior, and atmospheric composition. In some cases, variations in a planet's motion can provide clues about its internal structure, suggesting the presence of a liquid layer beneath the surface. Future missions and telescopes may be able to analyze the atmospheres of these distant ice worlds in more detail. If plumes or atmospheric signatures similar to those seen on Enceladus exist, they could provide strong evidence for subsurface oceans. In addition, advances in spectroscopy may allow scientists to detect chemical compounds associated with water and organic chemistry. The study of ice worlds also has important implications for our understanding of planetary diversity. These worlds represent a completely different category of habitability compared to Earth-like planets and ocean worlds. Instead of relying on surface conditions and sunlight, they depend on internal heat and geological activity. This expands the definition of where life might exist and shows that habitable environments can arise in unexpected places. Ice worlds with hidden oceans also challenge our assumptions about visibility and detection. Some of the most potentially habitable environments in the universe may be completely invisible from the outside. A planet that appears frozen and inactive may in fact contain a vast, dynamic ocean beneath its surface. This hidden complexity suggests that the universe may be far more biologically diverse than it appears at first glance. As exploration continues, these worlds will remain a major focus of scientific interest. They represent environments where life could exist in isolation, protected from external hazards and sustained by internal energy sources. They also provide natural laboratories for studying the limits of life and the conditions under which it can arise. In the broader search for alien life, ice worlds with hidden oceans remind us that habitability does not always require sunlight, surface warmth, or Earth-like conditions. Instead, life may find ways to emerge and persist in hidden environments deep beneath frozen surfaces, sustained by the quiet heat of planetary interiors and the slow chemistry of water and rock. These worlds expand our understanding of what is possible in the universe. They show that even the coldest and most distant regions of planetary systems may hold secrets of life, waiting beneath layers of ice, hidden from view but potentially alive with chemical and geological activity. In the vast diversity of planets that exist across the galaxy, not all worlds are calm, stable, or even remotely Earth-like. Some planets exist in conditions so extreme that they push the boundaries of physics, chemistry, and our imagination. Among these are lava worlds and extreme environment. Planets, places where surfaces are melted into oceans of molten rock, atmospheres are saturated with vaporized minerals, and temperatures reach levels that would instantly destroy any familiar form of matter on Earth. These worlds challenge our traditional idea of what a planet should be and reveal just how varied planetary systems can become. Lava worlds are typically found very close to their host stars. At such close distances, the amount of stellar radiation a planet receives is intense enough to strip away atmospheres, melt rocky surfaces, and vaporize surface materials. These planets often complete an orbit in just a few days or even less, placing them in extreme proximity to their stars. Because of this, their day side is constantly bombarded with intense heat and radiation, while their night side may experience relatively cooler but still extreme conditions. One of the defining features of lava worlds is the presence of vast molten surfaces. Instead of solid crusts, these planets may have oceans of magma stretching across their sun-facing sides. The temperatures are so high that rock itself becomes liquid, forming flowing rivers and seas of molten silicate material. These lava oceans are not stable in the way water oceans are on Earth. They are dynamic, constantly shifting as heat from the star interacts with the planet's surface and interior. In some lava worlds, the surface may not be completely molten everywhere. Instead, there may be a sharp contrast between the intensely hot day side and a slightly cooler night side. If the planet is tidally locked, meaning one side always faces the star, this contrast becomes even more extreme. The day side can become a permanent hemisphere of molten rock, while the night side may allow some materials to solidify, creating a complex and unstable boundary between liquid and solid regions. The atmosphere of a lava world is unlike anything found on Earth. At such high temperatures, even solid rock can vaporize, releasing minerals such as sodium, silicon monoxide, and iron vapor into the atmosphere. This creates a thin but chemically rich environment filled with evaporated rock particles. In some cases, these atmospheres can form temporary clouds of metal vapor that circulate around the planet before cooling and condensing on the night side. The boundary between the day side and night side of a lava world can create extreme weather systems. Vaporized rock from the hot side can travel across the atmosphere and then condense into solid particles on the cooler side, potentially forming mineral rain or dust storms made of rock fragments. This constant cycle of vaporization and condensation creates a highly dynamic and unstable planetary environment. Despite their extreme conditions, lava worlds provide valuable insights into planetary physics. They allow scientists to study how materials behave at temperatures far beyond those found on Earth. At such high temperatures, familiar geological processes break down and new forms of planetary behavior emerge. For example, the concept of a solid crust becomes less meaningful when the surface is constantly melting and reforming. One of the most important questions about lava worlds is how long they can remain in such extreme states. Over time, intense stellar radiation can strip away their atmospheres and gradually erode their mass. Some lava worlds may be the remnants of larger planets that were slowly boiled down by their proximity to their star. Others may be in temporary states, slowly cooling or migrating outward to more stable orbits. Lava worlds also help scientists understand the limits of planetary habitability. They represent the extreme opposite of habitable zone planets. Instead of being too cold for liquid water, they are far too hot for any known form of chemistry associated with life as we understand it. Organic molecules cannot survive in such environments, and any potential biological processes would be instantly destroyed by the intense heat. However, studying these extreme environments is still important because it helps define the boundaries of planetary systems. By understanding where habitability ends, scientists can better understand where it might begin. Lava worlds serve as natural laboratories for studying high-temperature chemistry, atmospheric escape, and planetary evolution under extreme conditions. Beyond lava worlds, there exists an even broader category of extreme environment planets. These are worlds that may not fit neatly into a single classification, but instead represent a wide range of harsh and unusual conditions. Some of these planets are exposed to intense radiation from their stars or nearby cosmic sources. Others may experience extreme pressure unusual atmospheric compositions, or highly unstable orbital dynamics. One example of extreme environment planets includes those orbiting very close to highly active stars. These stars may emit strong stellar flares, bursts of radiation, and powerful stellar winds. Planets in such systems are constantly bombarded by energetic particles that can strip away atmospheres and alter surface chemistry. In some cases, the radiation environment is so intense that it prevents stable atmospheres from forming at all. Another type of extreme environment planet includes those with highly eccentric orbits. These planets move in elongated paths around their stars, causing dramatic changes in temperature throughout their orbit. At one point in their orbit, they may be extremely close to their star, experiencing intense heating. At another point, they may be far away, plunging into deep cold. This creates cycles of extreme heating and cooling that can drastically reshape their surfaces over time. There are also planets that exist in multi-star systems, where gravitational interactions between multiple stars create complex and unstable environments. In such systems, planets may experience varying levels of radiation and gravitational forces depending on their position relative to each star. This can lead to unpredictable climates and orbital dynamics that are very different from those in single star systems like our own. Some extreme environment planets may also have unusual atmospheric compositions. Instead of nitrogen and oxygen like Earth, their atmospheres may be dominated by hydrogen, helium, carbon dioxide, sulfur compounds, or even vaporized metals. These atmospheres can behave in ways that are very different from Earth's weather systems, creating clouds of exotic materials and storms driven by unfamiliar physical processes. The study of these extreme worlds is important because it reveals the full range of planetary diversity in the universe. For a long time, scientists assumed that planets similar to those in our solar system were the most common. But exoplanet discoveries have shown that nature is far more creative and diverse than expected. Planets can exist in conditions that are far hotter, colder, more volatile, or more chemically unusual than anything seen in our own system. Even though lava worlds and extreme planets are unlikely to host life, they still play an important role in the evolution of planetary systems. They provide insight into how planets migrate, how atmospheres are lost or transformed, and how extreme energy environments shape planetary surfaces. They also help scientists understand the full range of outcomes that can occur during planet formation. In some cases, extreme environment planets may represent transitional stages in planetary evolution. A planet that is currently a lava world may eventually cool and develop a solid crust if it moves farther from its star. Conversely, a previously stable planet may become a lava world if its orbit changes or its star evolves. These transitions show that planets are not static objects, but dynamic systems that change over time. The discovery of these extreme worlds also has implications for the search for life. While they are not considered habitable, they help define the outer boundaries of habitability. By understanding where conditions become too extreme for life to survive, scientists can better identify regions where life is more likely to exist. In addition, studying extreme environments on other planets helps scientists understand similar processes on Earth under past or future conditions. Early Earth may have experienced periods of extreme heat and volcanic activity, while future changes in the sun's brightness could alter Earth's climate over long timescales. In this way, lava worlds and extreme planets provide a window into planetary processes that can affect all worlds, including our own. As observational technology improves, scientists are beginning to detect more of these extreme planets in detail. By studying their atmospheres, thermal emissions, and orbital characteristics, researchers can build a more complete picture of how such environments function. Future telescopes will allow even more precise measurements, revealing the chemical and physical processes occurring on their surfaces. In the broader context of planetary science, lava worlds and extreme environment, planets represent the outer limits of what planets can be. They show what happens when a planet is pushed to its physical extremes, whether through intense heat, radiation, or gravitational forces. They are reminders that the universe is not only capable of creating worlds like Earth, but also worlds that exist in conditions far beyond human experience. These planets expand our understanding of planetary systems and highlight the incredible diversity of environments that exist across the galaxy. From oceans of molten rock to atmospheres filled with vaporized minerals, they reveal a universe filled with worlds that are constantly shaped by powerful and often violent forces. In studying these extreme environments, scientists gain not only knowledge of distant planets, but also a deeper appreciation for the delicate balance that allows Earth to remain stable and habitable. Lava worlds and extreme planets stand as cosmic examples of what happens when that balance is pushed to its limits, showing us the full spectrum of planetary possibility. One of the most powerful breakthroughs in the study of alien worlds is not the discovery of new planets themselves, but the ability to study what those planets are made of. For most of human history, planets beyond our solar system were nothing more than points of light hidden in the glare of their host stars. We could measure their presence indirectly, but we had no way to understand their surfaces, their atmospheres, or their chemical makeup. That changed when astronomers developed techniques to study exoplanet atmospheres, opening a new window into the nature of distant worlds and bringing us closer than ever to understanding whether any of them could support life. The atmosphere of a planet is one of its most important features. It is not just a layer of gas surrounding a world. It is a dynamic system that controls temperature, distributes energy, shapes weather patterns, and interacts with the surface and interior of the planet. On Earth, the atmosphere is essential for life. It provides oxygen for respiration, protects the surface from harmful radiation, and maintains stable climate conditions through the greenhouse effect. Without an atmosphere, Earth would be a frozen, airless rock exposed to the harsh conditions of space. When scientists began searching for exoplanets, they quickly realized that understanding atmospheres would be key to identifying potentially habitable worlds. A planet's size and orbit could tell us where it is located and how big it is, but its atmosphere reveals what kind of environment actually exists on its surface. However, studying something so distant and faint posed an enormous challenge. Exoplanets are extremely small compared to their host stars, and their atmospheres are even more difficult to detect directly. The breakthrough came through a method known as transit spectroscopy. This technique relies on the observation of a planet passing in front of its star, an event called a transit. During a transit, a small portion of the star's light filters through the planet's atmosphere before reaching Earth. As this light passes through the atmospheric gases, certain wavelengths are absorbed or altered depending on the chemical composition of the atmosphere. By carefully analyzing these changes in light, scientists can determine what gases are present in the atmosphere of the distant planet. This method is incredibly precise and requires extremely sensitive instruments. Even though the amount of light passing through an exoplanet's atmosphere is tiny, it carries a chemical fingerprint that can be detected using advanced telescopes and spectrographs. Each element and molecule absorbs light at specific wavelengths, creating a unique pattern known as a spectrum. By comparing the observed spectrum with known laboratory data, scientists can identify gases such as water vapor, carbon dioxide, methane, sodium, and even more complex molecules. The detection of water vapor in an exoplanet's atmosphere is particularly significant. Water is one of the most important ingredients for life as we know it. Its presence suggests that the planet may have conditions capable of supporting liquid water on its surface, although this is not guaranteed. Water vapor can exist in many types of environments, including extremely hot or cold atmospheres, so additional data is needed to determine whether a planet is truly habitable. Carbon dioxide is another important atmospheric component. On Earth, it plays a crucial role in regulating temperature through the greenhouse effect. On other planets, high levels of carbon dioxide can lead to extreme warming, creating conditions similar to those on Venus, where a thick carbon dioxide atmosphere traps heat and produces surface temperatures hot enough to melt lead. The detection of carbon dioxide in exoplanet atmospheres helps scientists understand how energy is balanced on distant worlds. Methane is one of the most interesting gases detected in some exoplanet atmospheres. On Earth, methane is produced by both geological and biological processes. It can be released from volcanic activity, but it is also produced by living organisms such as microbes. Because of this dual origin, the presence of methane alone is not enough to confirm life, but when found alongside other gases in unusual combinations, it can become a potential biosignature. Scientists carefully study the ratios of gases like methane, oxygen, and carbon dioxide to look for patterns that might indicate biological activity. Sodium and potassium have also been detected in some exoplanet atmospheres. These elements are often found in the atmospheres of hot planets where high temperatures cause them to vaporize from the surface. Their presence provides information about atmospheric temperature and structure, helping scientists understand the physical conditions on these distant worlds. As observational technology has improved, scientists have been able to move beyond simple detection and begin studying atmospheric dynamics. This includes understanding how winds, temperature differences, and chemical reactions shape the behavior of a planet's atmosphere. For example, on tidally locked planets, where one side always faces the star, there can be extreme temperature differences between the day and night sides. This can create powerful winds that transport heat across the planet, influencing global climate patterns. Some exoplanet atmospheres show signs of high-altitude clouds or hazes. These layers can obscure the deeper atmosphere and make it more difficult to detect chemical signatures. Clouds can be composed of a wide range of materials depending on the temperature of the planet, including water droplets, sulfuric acid, silicate particles, or even metal compounds in extremely hot environments. These clouds play an important role in reflecting or absorbing light and can significantly affect a planet's climate. One of the most fascinating aspects of exoplanet atmospheric research is the ability to study weather on distant worlds. While we cannot observe weather systems directly in real time, variations in atmospheric data can reveal changes in temperature, composition, and circulation patterns. Some planets may experience constant storms driven by intense heat from their stars, while others may have more stable climates depending on their atmospheric composition and orbital characteristics. The study of atmospheres also provides clues about a planet's history. A planet's atmosphere is not static. It evolves over time due to volcanic activity, chemical reactions, stellar radiation, and interactions with space. For example, a planet that once had a thick atmosphere may lose it over time if it is exposed to strong stellar winds. Conversely, a planet with active volcanism may gradually build up a dense atmosphere through outgassing from its interior. Atmospheric escape is one of the key processes that shapes planetary evolution. When a planet is exposed to high-energy radiation from its star, the upper layers of its atmosphere can become heated and expand into space. Over long periods of time, this can cause lighter gases such as hydrogen and helium to escape, leaving behind heavier elements. This process can dramatically change the composition and density of a planet's atmosphere. Magnetic fields also play an important role in protecting atmospheres from being stripped away. A strong magnetic field can deflect charged particles from the stellar wind, reducing atmospheric loss. On planets without strong magnetic fields, atmospheres may erode more quickly, especially if the planet is close to its star. This interaction between magnetic fields and stellar radiation is an important factor in determining long-term habitability. The study of exoplanet atmospheres is still in its early stages, but it has already transformed our understanding of planetary systems. We now know that planets can have a wide range of atmospheric compositions and behaviors far beyond what we see in our own solar system. Some planets have thick hydrogen-rich atmospheres, while others have thin, rocky exospheres or dense clouds of exotic materials. Future telescopes will greatly expand our ability to study these atmospheres in detail. Instruments capable of directly imaging exoplanets will allow scientists to analyze reflected light from their surfaces and atmospheres, providing even more detailed information about their composition. This will enable the detection of smaller molecules and potentially even more complex chemical signatures. One of the ultimate goals of atmospheric research is the detection of biosignatures, chemical indicators that may suggest the presence of life. On Earth, life has dramatically altered the composition of the atmosphere, producing oxygen and other gases that would otherwise be rare. If similar patterns are detected on exoplanets, it could provide strong evidence for biological activity. However, distinguishing between biological and non-biological processes remains one of the greatest challenges in the field. The study of exoplanet atmospheres also helps scientists understand the diversity of planetary environments in the galaxy. No two planets are exactly alike. Each atmosphere reflects a unique combination of formation history, chemical processes, and environmental conditions. This diversity suggests that the universe is filled with a wide range of planetary climates, some familiar and others completely alien. As research continues, atmospheres will remain one of the most important tools for exploring alien worlds. They provide a direct link between distant planets and the physical processes that shape them. Through the analysis of starlight, scientists are beginning to uncover the hidden chemistry of worlds that are light years away, revealing details that were once thought to be completely beyond our reach. In the search for life beyond Earth, exoplanet atmospheres are one of the most promising sources of information. They carry the signatures of chemical processes, environmental conditions, and possibly even biological activity. Each new discovery brings us closer to understanding whether Earth is unique or part of a vast collection of living worlds scattered throughout the galaxy. The study of these distant atmospheres is not just about identifying gases or measuring temperatures. It is about decoding the story of each planet, understanding how it formed, how it evolved, and what conditions exist today. In every spectrum of light that passes through an alien atmosphere, there is a hidden narrative waiting to be read, a story of chemistry, physics, and perhaps even life itself, unfolding on a world far beyond our own. As the search for alien worlds continues to expand, scientists have begun to realize that planets are not the only places where life might exist. In fact, some of the most promising environments in the universe may not be planets at all, but moons orbiting giant planets. These natural satellites, often overlooked in early planetary science, have emerged as serious candidates in the search for extraterrestrial life. Moons that could host life represent a category of worlds that combine geological activity, hidden oceans, and unique energy sources in ways that challenge traditional ideas of habitability. In our own solar system, moons were once considered simple, inactive bodies. They were thought to be frozen, airless, and geologically dead compared to planets. However, as space exploration advanced, this view changed dramatically. Missions to Jupiter and Saturn revealed that several of their moons are far more active and complex than previously believed. Some of them have internal oceans, volcanic activity, and dynamic surfaces shaped by powerful gravitational forces. One of the most important discoveries in this area is the realization that large moons can retain internal heat over long periods of time. This heat is often generated by tidal forces, which occur when a moon is gravitationally stretched and compressed by its parent planet. As the moon orbits a massive planet, the gravitational pull on different parts of the moon changes slightly, causing it to flex. This constant flexing generates friction inside the moon's interior, producing heat that can melt ice and maintain subsurface oceans. This process of tidal heating is particularly important for moons that orbit giant planets like Jupiter and Saturn. These planets have extremely strong gravitational fields, which can create significant tidal effects on nearby moons. Over time, this energy input can be enough to keep large volumes of water in a liquid state beneath icy crusts, even in regions of space that are far too cold for liquid water to exist on the surface. One of the most famous examples of such a moon is Europa, one of Jupiter's largest satellites. Europa has a smooth, icy surface marked by cracks and ridges, suggesting that the ice is constantly shifting and moving. Beneath this frozen crust, scientists believe there is a global subsurface ocean of liquid water. This ocean may be in direct contact with a rocky seafloor, creating conditions that could allow for chemical interactions similar to those that support life in Earth's deep oceans. Another important example is Enceladus, a small moon of Saturn. Enceladus has captured scientific attention because it actively ejects plumes of water vapor and ice particles from its south polar region. These plumes are believed to originate from a subsurface ocean beneath the icy crust. When spacecraft pass through these plumes, they can directly sample material from the interior of the moon. Analysis of these samples has revealed the presence of water, organic molecules, and signs of hydrothermal activity. These discoveries have fundamentally changed how scientists think about habitability. It is no longer necessary for a world to be within a star's habitable zone to have liquid water. Instead, internal heating processes can create localized environments where liquid water exists, even in extremely cold regions of space. This greatly expands the number of potential habitable environments in the universe. The possibility that moons could host life is especially important when considering exoplanetary systems. Many giant planets have been discovered orbiting distant stars, and it is reasonable to assume that these planets may also have large moon systems. If even a fraction of these moons have conditions similar to Europa or Enceladus, then the number of potentially habitable environments in the galaxy could increase dramatically. Moons that could host life are not limited to icy environments. Some moons may have rocky surfaces with volcanic activity driven by tidal heating. These volcanic moons could have atmospheres, surface chemistry, and energy sources that create complex and dynamic environments. In such cases, the moon itself becomes a miniature world with its own geological and atmospheric processes. The interaction between a moon and its host planet plays a crucial role in shaping its environment. A large gas giant exerts strong gravitational forces not only on its moons, but also on the surrounding space environment. This can create radiation belts, magnetic interactions, and particle flows that influence the surface and atmosphere of the moon. While these conditions can be harsh, they also contribute to the energy balance that drives internal heating and geological activity. One of the key advantages of moons as potential habitats is their stability over long timescales. Unlike planets that may experience dramatic changes in their orbits or stellar environments, moons often remain in stable orbits around their host planets for billions of years. This long-term stability provides a consistent environment where life, if it exists, could potentially develop and evolve. Another important factor is the presence of subsurface oceans. On many icy moons, these oceans are completely hidden beneath thick layers of ice, protecting them from external radiation and temperature fluctuations. This creates isolated environments that are shielded from space, similar in some ways to deep underground ecosystems on Earth. These subsurface oceans may contain the right combination of water, energy, and chemical elements needed for life. The chemistry of these hidden oceans is a subject of intense scientific interest. On Earth, life depends on a wide range of chemical elements, including carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur. If these elements are present in subsurface oceans, and if energy sources are available, then the basic ingredients for life could exist. Hydrothermal activity at the ocean floor could provide additional energy and nutrients, creating environments similar to Earth's deep-sea ecosystems. One of the most intriguing aspects of moons as potential habitats is the possibility of life existing in complete darkness. Without sunlight, life would need to rely on chemical energy rather than photosynthesis. This type of life is already known to exist on Earth in deep ocean environments. Organisms near hydrothermal vents use chemical reactions involving hydrogen sulfide and other compounds to produce energy. If similar processes occur on icy moons, then life could potentially exist without any dependence on sunlight. Detecting life on distant moons is extremely challenging. Because these environments are hidden beneath ice layers or embedded within complex planetary systems, direct observation is often impossible with current technology. Instead, scientists rely on indirect evidence, such as surface features, plume activity, and chemical signatures. For example, the detection of organic molecules in Enceladus's plumes suggests that complex chemistry is occurring within its subsurface ocean. Future missions to moons in our solar system aim to explore these environments in greater detail. Spacecraft may be sent to fly through plumes, land on icy surfaces, or even drill through ice layers to access subsurface oceans. These missions could provide direct evidence of whether life exists beyond Earth in our own planetary system. When it comes to exoplanets, the study of moons is still in its early stages. Detecting moons around distant planets is extremely difficult due to their small size and faint signals. However, as observational techniques improve, scientists are beginning to develop methods for identifying exomoons. These include analyzing variations in transit timing and studying subtle changes in planetary motion caused by the gravitational influence of moons. If large exomoons are discovered, they could become some of the most important targets in the search for extraterrestrial life. A moon orbiting within the habitable zone of its star, or even a moon with internal heating from tidal forces, could provide a stable and potentially habitable environment. In some cases, exomoons may even be more suitable for life than their parent planets. The diversity of moons in our solar system suggests that similar diversity may exist in other planetary systems. Some moons may be small and icy, others large and rocky, and still others geologically active with thick atmospheres. This wide range of possibilities makes moons an important and expanding field of study in astrobiology. Moons that could host life also challenge our traditional definition of a habitable world. Habitability is no longer limited to planets orbiting within a star's habitable zone. Instead, it can also include smaller bodies influenced by internal heating and gravitational interactions. This broader definition greatly increases the number of potential habitats in the universe. In the search for alien life, moons represent a shift in perspective. They remind us that life may not be confined to Earth-like planets with familiar conditions. Instead, it may exist in hidden oceans beneath ice, in volcanic environments shaped by tidal forces, or in chemically rich systems far from direct sunlight. As exploration continues, moons will remain a central focus of scientific investigation. They offer some of the most promising environments for discovering life beyond Earth, both within our solar system and potentially around distant stars. Each new discovery brings us closer to understanding the true diversity of habitable environments in the universe. In the vast landscape of space, moons are no longer seen as secondary worlds. They are now recognized as complex, dynamic systems with the potential to host life in unexpected ways. Whether hidden beneath ice or shaped by volcanic activity, these worlds expand our understanding of where life might exist and how it might emerge under conditions very different from those on Earth. As humanity's exploration of alien worlds advances, one of the most important goals is no longer just finding planets or moons that might support life, but actually identifying signs that life may already exist. This search focuses on what scientists call biosignatures, chemical or physical indicators that could suggest biological activity on a distant world. Biosignatures represent one of the most profound frontiers in science because they move the question of extraterrestrial life from speculation toward potential detection. The idea of biosignatures is based on a simple principle. Life, as we understand it, interacts with its environment in ways that leave measurable traces. On Earth, life has dramatically altered the composition of the atmosphere, oceans, and even the geology of the planet. For example, the presence of oxygen in Earth's atmosphere is largely the result of biological activity. Without life, Earth's atmosphere would be very different, likely dominated by gases such as carbon dioxide and nitrogen with very little free oxygen. This realization led scientists to ask a crucial question. If life exists on other planets, could it also leave detectable chemical fingerprints in their atmospheres or surfaces? The answer is yes, at least in principle. Certain gases and chemical combinations are difficult to maintain in equilibrium without continuous replenishment. If such gases are detected on an exoplanet, they may indicate the presence of active processes that could be biological in origin. One of the most well-known biosignature gases is oxygen. On Earth, oxygen is constantly produced by photosynthetic organisms such as plants, algae, and certain bacteria. Oxygen is highly reactive, meaning it tends to combine with other elements and disappear from the atmosphere unless it is continuously replenished. Because of this, the presence of large amounts of oxygen in a planet's atmosphere could suggest that some form of life is actively producing it. However, oxygen alone is not a definitive sign of life. There are non-biological processes that can also produce oxygen under certain conditions, such as the breakdown of water vapor by ultraviolet radiation. This means that scientists must look for additional context when interpreting oxygen as a potential biosignature. Another important biosignature gas is methane. On Earth, methane is produced by both biological and geological processes. Microorganisms known as methanogens produce methane as part of their metabolic activity, particularly in environments such as wetlands and the digestive systems of animals. At the same time, methane can also be released from volcanic activity and chemical reactions in the planet's crust. Because of this dual origin, methane is considered a potential biosignature only when found in specific combinations with other gases. One of the most interesting combinations is the simultaneous presence of oxygen and methane in significant quantities. On Earth, these two gases normally react with each other and do not coexist in large amounts without continuous replenishment. If such a combination were detected in an exoplanet atmosphere, it could suggest that active processes are maintaining this chemical imbalance, potentially indicating biological activity. Carbon dioxide is another important component in the search for biosignatures. While it is not directly considered a sign of life, its abundance can provide important context about a planet's climate and atmospheric chemistry. On Earth, carbon dioxide plays a key role in regulating temperature through the greenhouse effect. On other planets, high levels of carbon dioxide can indicate either volcanic activity or atmospheric conditions that may not be suitable for life as we know it. Water vapor is also a crucial molecule in biosignature studies. While it is not itself a sign of life, it is essential for habitability. The presence of water vapor in an exoplanet's atmosphere suggests that liquid water may exist somewhere on the planet's surface or subsurface. Since liquid water is considered one of the fundamental requirements for life on Earth, its presence is an important factor in assessing a planet's potential habitability. Beyond individual gases, scientists also study more complex chemical patterns known as atmospheric disequilibrium. This occurs when a planet's atmosphere contains combinations of gases that should not normally coexist under equilibrium conditions. On Earth, this disequilibrium is largely maintained by biological processes. For example, the coexistence of oxygen, methane, and nitrogen in Earth's atmosphere is largely driven by life. Detecting similar disequilibrium on another planet could be one of the strongest indicators of biological activity. Another class of potential biosignatures includes surface features. On Earth, life has shaped the planet's surface in many ways, from large-scale vegetation patterns to microbial mats that influence mineral formations. If telescopes become powerful enough to resolve surface details on exoplanets, scientists may be able to detect patterns that are difficult to explain without biological activity. For example, seasonal changes in surface reflectivity could suggest the presence of plant-like organisms. However, interpreting surface features on distant worlds is extremely challenging. Many non-biological processes can also create complex surface patterns. Volcanic activity, erosion, and chemical weathering can all produce structures that might resemble biological signatures. Because of this, surface biosignatures are considered more speculative than atmospheric ones. One of the most promising areas of biosignature research involves studying exoplanet atmospheres using advanced spectroscopy. By analyzing the light that passes through or is reflected by a planet's atmosphere, scientists can detect the presence of specific molecules. Future telescopes will be able to observe smaller planets in greater detail, potentially allowing for the detection of biosignature gases in Earth-sized exoplanets orbiting distant stars. One of the major challenges in biosignature detection is avoiding false positives. A false positive occurs when a chemical signature appears to indicate life, but is actually produced by non-biological processes. For example, oxygen can be produced by the photodissociation of water vapor, and methane can be produced by geological activity. To address this challenge, scientists use multiple lines of evidence and look for combinations of gases that are difficult to explain without life. Another challenge is false negatives. These occur when life is present on a planet but does not produce detectable biosignatures. Life on other worlds may not resemble life on Earth, and it may not produce the same gases or chemical signals. For example, life in subsurface oceans or deep underground environments may have little or no interaction with the atmosphere, making it extremely difficult to detect using remote observations. Because of these challenges, biosignature research is highly cautious and relies on statistical and comparative methods. Scientists study a wide range of planetary environments to understand how different processes can produce similar chemical signatures. By building a large database of planetary atmospheres, they can improve their ability to distinguish between biological and non-biological sources. In addition to gases and surface features, scientists are also exploring the possibility of detecting temporal changes as biosignatures. On Earth, biological activity often varies over time, creating seasonal or diurnal cycles in atmospheric composition. If similar cycles were detected on exoplanets, they could provide additional evidence for biological processes. For example, seasonal changes in methane or oxygen levels might suggest active biological sources. The search for biosignatures is closely linked to the study of habitability. A planet must first have conditions suitable for life before it can produce detectable biosignatures. This includes the presence of liquid water, a stable atmosphere, and an energy source. Without these conditions, the likelihood of life is extremely low, and biosignatures would not be expected. One of the most important goals in future space exploration is the direct imaging of Earth-like exoplanets. This would allow scientists to observe the light reflected from a planet's surface and atmosphere without interference from its host star. By analyzing this light, it may be possible to detect biosignatures directly and study the characteristics of potentially habitable worlds in detail. The development of more advanced telescopes and instruments is bringing this goal closer to reality. Space-based observatories and ground-based telescopes with advanced adaptive optics are improving our ability to detect and analyze exoplanet atmospheres. As these technologies continue to improve, the detection of biosignatures may become one of the most significant milestones in the history of science. The implications of discovering a biosignature on an exoplanet would be profound. It would suggest that life is not unique to Earth and may be common in the universe. Even the detection of simple microbial life would fundamentally change our understanding of biology, evolution, and the distribution of life in the cosmos. However, scientists remain cautious. The detection of a potential biosignature would require extensive verification and multiple independent observations before any conclusions could be drawn. The goal is not to rush to conclusions, but to carefully build a strong case based on multiple lines of evidence. In the broader context of astrobiology, biosignatures represent the bridge between planetary science and the study of life itself. They connect the physical and chemical properties of planets with the possibility of biological activity. By studying biosignatures, scientists are not only searching for life, but also learning how to recognize it in environments that may be very different from Earth. As our understanding of alien worlds continues to grow, biosignatures will remain one of the most important tools in the search for extraterrestrial life. They represent the subtle clues that life leaves behind, hidden in the light of distant stars and the chemistry of faraway atmospheres. Each new discovery brings us closer to answering one of humanity's oldest questions. Are we alone in the universe, or is life a common feature of the cosmos? Biosignatures may one day provide the answer, revealing that life is not confined to Earth, but is instead a widespread phenomenon woven into the fabric of the universe itself. As the search for alien worlds reaches new levels of precision and ambition, humanity stands at the threshold of a new era in exploration. The study of exoplanets, once limited to indirect detection and theoretical models, is rapidly evolving into a detailed science capable of analyzing the chemistry, climate, and potential habitability of distant worlds. The future of alien world exploration is not just about finding more planets, but about understanding them in greater depth than ever before, and possibly answering one of the most profound questions in human history: whether we are alone in the universe. The next generation of telescopes will play a central role in this transformation. Ground-based observatories are becoming larger and more advanced, equipped with adaptive optics systems that correct for atmospheric distortion and allow for sharper images of distant stars and planets. At the same time, space-based telescopes are being designed to observe the universe without the interference of Earth's atmosphere, providing clearer and more stable views of exoplanet systems. One of the most important goals of these future instruments is the direct imaging of Earth-like exoplanets. Until now, most exoplanets have been detected indirectly through methods such as transits or radial velocity measurements. These techniques provide valuable information about a planet's size, mass, and orbit, but they do not allow scientists to see the planet directly. Direct imaging would change this completely by allowing astronomers to capture actual light from the planet itself, separating it from the overwhelming brightness of its host star. Achieving this goal is extremely challenging, because stars are billions of times brighter than the planets that orbit them. To overcome this, scientists are developing advanced technologies such as coronagraphs and starshades. A coronagraph is an instrument that blocks out the light of a star within a telescope, allowing faint surrounding objects like planets to become visible. A starshade is a separate spacecraft designed to fly in precise alignment with the telescope, blocking starlight before it even enters the telescope's optics. Together, these technologies could make it possible to observe Earth-sized planets orbiting distant stars. Once direct imaging becomes possible, scientists will be able to study exoplanets in unprecedented detail. They will be able to analyze reflected light from planetary surfaces, observe atmospheric composition directly, and track changes in climate and weather patterns over time. This will allow for a much deeper understanding of planetary environments and their potential to support life. One of the key objectives of future exploration is the identification of truly Earth-like worlds. These are planets that not only exist in the habitable zone of their stars, but also have similar sizes, atmospheric compositions, and surface conditions to Earth. Finding such a planet would represent one of the most important discoveries in the history of science. It would provide a natural laboratory for studying the conditions under which life might arise and evolve elsewhere in the universe. In addition to Earth-like planets, future missions will also focus on a wide range of other interesting worlds. These include ocean worlds, super-Earths, ice-covered planets, and even rogue planets that drift through interstellar space without orbiting any star. Each of these categories represents a different type of environment where unusual physical and chemical processes may occur. Rogue planets are particularly intriguing because they exist in complete darkness, far from any stellar energy source. Despite this, some of them may still retain internal heat, potentially allowing subsurface oceans to exist beneath thick ice layers. These hidden environments could, in theory, support life in ways that are completely independent of starlight. If such worlds exist in large numbers, they could represent a hidden population of habitable environments scattered throughout the galaxy. Another major focus of future exploration is the study of planetary atmospheres in greater detail. Advanced spectroscopic techniques will allow scientists to detect smaller and more complex molecules in exoplanet atmospheres. This will improve the ability to search for biosignatures and understand the chemical diversity of planetary systems. It will also help identify planets with unusual or unexpected atmospheric compositions that could reveal new types of planetary environments. One of the most ambitious goals in this field is the detection of true biosignatures on an exoplanet. While current research focuses on identifying potential indicators of life, future observations may be able to confirm the presence of biological activity beyond Earth. This would require multiple lines of evidence, including atmospheric chemistry, surface conditions, and possibly even temporal changes consistent with biological cycles. If such a discovery were made, it would represent a turning point in human history. It would confirm that life is not unique to Earth and may exist throughout the universe in many different forms. Even the discovery of simple microbial life would have profound implications for biology, evolution, and our understanding of the cosmos. However, the search for life is only one part of the future of alien world exploration. Scientists are also interested in understanding the full diversity of planetary systems. This includes studying how planets form, migrate, and evolve over time. By observing large numbers of exoplanets at different stages of development, researchers can build a more complete picture of how planetary systems change over billions of years. Planetary migration is one of the key processes that shapes the architecture of planetary systems. In many cases, planets do not remain in the positions where they originally formed. Instead, gravitational interactions with other planets, or the protoplanetary disk, can cause them to move inward or outward over time. This process can create systems that look very different from our own solar system, with giant planets close to their stars or tightly packed systems of multiple rocky planets. Understanding these processes is essential for interpreting the diversity of exoplanets that have already been discovered. It also helps scientists predict what types of planets might exist in systems that have not yet been fully observed. Future exploration will also focus on the study of planetary interiors. While most observations are limited to a planet's surface or atmosphere, understanding the internal structure of planets is equally important. The composition of a planet's core, mantle, and crust can influence its magnetic field, volcanic activity, and long-term habitability. Advances in observational techniques may eventually allow scientists to infer internal structures based on subtle measurements of a planet's mass, density, and gravitational interactions. Another exciting direction for future research is the study of exomoons. These are moons that orbit planets outside our solar system. While no exomoon has yet been confirmed with certainty, their existence is highly likely given the abundance of moons in our own solar system. Exomoons could themselves be habitable, especially if they orbit within the habitable zones of their stars or experience internal heating from tidal forces. This expands the range of potential habitable environments even further. The search for alien worlds is also closely connected to advancements in artificial intelligence and data analysis. Modern telescopes generate enormous amounts of data, far too much for humans to analyze manually. Machine learning algorithms are increasingly being used to identify patterns, detect exoplanet signals, and classify planetary systems. These tools help scientists process vast datasets more efficiently and uncover subtle signals that might otherwise be missed. As exploration continues, international collaboration will play a crucial role. Space agencies and research institutions around the world are working together to design and launch missions dedicated to exoplanet research. This global effort reflects the shared nature of the question being asked. Whether life exists beyond Earth is not just a scientific question, but a fundamental inquiry about our place in the universe. The future may also bring missions designed to study nearby star systems directly. While most known exoplanets are located many light-years away, some relatively nearby systems could become targets for detailed study. In the more distant future, advanced propulsion technologies might even make it possible to send probes to nearby exoplanetary systems, providing direct measurements of alien worlds. Even if interstellar travel remains far beyond our current capabilities, remote sensing technologies will continue to improve. Each new generation of telescopes will reveal more about the structure and composition of distant planets, gradually building a more complete picture of the galaxy. In the broader context of human knowledge, the exploration of alien worlds represents one of the most significant scientific journeys ever undertaken. It combines astronomy, physics, chemistry, geology, and biology into a unified effort to understand the universe beyond Earth. It also challenges humanity to reconsider its assumptions about uniqueness, rarity, and the nature of life itself. Every new exoplanet discovered adds another piece to this cosmic puzzle. Some will be extreme and hostile, others may be calm and Earth-like, and some may exist in forms that are completely unexpected. Together, they form a vast and diverse population of worlds that reflects the complexity of planetary formation across the galaxy. The future of alien world exploration is ultimately about discovery in its most profound sense. It is about uncovering environments that have never been seen before, understanding processes that operate on scales far beyond human experience, and searching for signs that life may exist elsewhere in the universe. As technology advances and knowledge grows, humanity moves closer to a time when alien worlds are not just distant points of light, but fully understood environments with their own histories, climates, and possibly even living systems. Each step forward brings us closer to answering the ancient question that has guided so much of human curiosity. Are we alone, or is the universe filled with other worlds where life has also taken hold?